Here's our 475 final project. It's a topology optimization and FEA analysis of an office chair base. My name is Barrett Winrick.
And I'm Casey Ray.
We chose to do a chair base for this project in order to optimize the design so that it could withstand the forces of sitting on the chair without altering the performance. We did a topology optimization using hypermesh, and then we made a 3D model using NX9 that was then used for FEA analysis using ANSYS Workbench. Here you can see the workspace that we meshed and applied boundary conditions to, and here you can see the hypermesh optimization of the design space, removing density at low stress locations in order to produce the final shape that we would then use to model. From that design, we produced the final shape and geometry using NX9, and this model is what we would use for our finite element analysis. We exported it as a parasolid for use in ANSYS Workbench.
So in ANSYS, we decided to use steel as our material of choice for the FEA analysis. So we selected steel out of the material library within the program. You can see all of the values that are associated with this material. Next, we had to import the geometry that we created using NX. So we went and imported our parasolid file from before. And you can see it's please work since, well, it didn't work the first few times we tried. Well, many times. So here you can see it generates a very similar shape to what we modeled in NX as well as in the topology program. We can close out of the modeler, and now we can actually go into setting up the FEA. So here we have our model, and we need to place a mesh on it to start. To do this, we open up the mesh tool and simply click on the solid itself. So you can see we are using a triangular mesh with 6 nodes, and now we have to place the boundary conditions. First, we have a fixed point so that we don't have singular matrices, and we also fix the displacement of the very bottom of the shape in the z direction. Next, we put a pressure on the boss at the top of the structure. We selected a pressure that was in line with a 250-pound person. So here you can see we have all of our boundary conditions in place: the pressure, the fixed point, and the fixed bottom of the structure. And now we just solve. So we solved for displacement, stress, and strain. First we have the strain, and you can see the strain is very evenly distributed throughout the entire structure. This was due to the topology optimization and trying to evenly spread all the material throughout the structure. You can see that the peak strains are near the edges or the sharp corners of the structure. Finally, we have the displacement, and the displacement was applied using a ramp function over time, so we can actually see what happens to the deflection of the structure as the load is pressed. You can see that the legs spread out from each other, and the top actually lowers a little bit. The maximum displacement is on the opposite side of the structure as the fixed point.
And here you can see the FEA maximum values from our results. As you can see, the displacement, the equivalent stress, and the equivalent strain were all very low throughout the structure. In conclusion, the overall deformation of the structure was very small, the stress was evenly distributed throughout the structure, and this was due to the optimization process, which resulted in a very efficient use of material. Do you have any questions?